of the pole if it's negative. So this shows you that the logarithmic integral is discovering something both about zeros and also possibly about poles of a function, because this example does both. And it also reflects something about the winding number of the curve which you're integrating over. Yeah? So here is the argument principle number 1. Theorem. Argument principle 1. Let D be a bounded domain and piecewise smooth boundary, and F meromorphic. What did that mean? It's holomorphic except what? And on singularities, and what can you say about those singularities? Certain. They're isolated. Isolated, yes, except for a finite number of isolated singularities, each of which is a pole or removable. So no essential singularities, no branch cuts.
So that's what essential singularity is? It's a branch cut?
No, I didn't say that.
So what's the difference between an essential and an isolated?
I didn't say that an essential singularity wasn't an isolated. I just said that the meromorphic function doesn't have essential singularities. So the meromorphic function has isolated singularities which are only poles or removable singularities. You can't have an essential singularity. But an essential singularity is a specific kind of isolated singularity. A branch cut is a different thing. I mean, it's...
Is it similar to like every square rectangle or whatever it is?
Oh, you're not... I haven't taught math.
Rectangle's a square, but not every square.
I haven't taught math 200 yet. I don't know about that stuff. Let's see, your f of z not equal to 0 on boundary of D. I mean, it's not true. I taught it in 2009, but by now that knowledge is faded. All right, so then, no, like the branch cut is not, where the branch cut starts is not typically an isolated singularity. Like the singularity at the origin for the logarithm is by no means isolated. Like I can't look at a punctured disk on which it's holomorphic on the punctured disk at the origin, right? The logarithm necessarily has a breakdown at some branch cut, you know, so that the origin is not an isolated singularity of the logarithm, for example. Anyway, so 1 over 2 pi I f prime of z over f of z dz, what is this equal to? It is equal to n sub 0 minus n sub infinity. And what does that mean? Where n sub 0 is equal to the number of zeros of f of z in D, and n sub infinity is equal to the number of poles of f of z in D, counting multiplicities. All right. Let's see how that works. So let z naught be 0 of order n, right? Then you have f of z is z minus z naught to the power big N times h of z, right? Where h of z naught is not equal to 0. So then f prime of z over f of z is equal to, well, if we differentiate this, we get n times z minus z naught to the n minus 1, h of z, plus z minus z naught to the power n times h prime of z. I did the product rule, yeah? Product rule for f prime, and then I'm dividing by z minus z naught to the power n times h of z down here. And so if you clean that up, you're just left with n over z minus z naught plus h prime of z over h of z, right? Likewise, if z naught is pole of order n, then what is f of z equal to? We can do what? H of z divided by z minus z naught, right? This is the proof, yeah. So that's what f prime over f looks like at a 0 of order n. And what is f prime of z divided by f of z look at a pole of order n? Let's see here. So we'd have what? H prime of z over z minus z naught to the power n plus like h of z times what? Minus n over z minus z naught to the n plus 1, I believe. So if you multiply that top and bottom by z minus z naught to the n, I think it simplifies. The h of z's, they be canceling. You get a minus n over z minus z naught from the term where the h of z's cancel. And the other one, oh, notice that the reciprocal terms cancel and you get plus. That's kind of funny, right? That's actually really kind of funny. Look at that. Compare this to that. Very similar, right? But there's a difference, the sign, right? Plus, minus. So what does this all show? In summary, we see that the residue of f prime of z over f of z. I guess my statement about this having nothing to do with residue theory was premature. Z naught, it's just been a minute since I taught this stuff. So f prime of z over f of z is equal to, well, apparently plus or minus n, right? Depending on whether we're talking about a 0 of order n or a pole of order n. So if it's meromorphic, what does that give to us? Finite number of isolated singularities, right? So if we calculate the integral around the boundary of D of f prime of z over f of z dz, remember that by the residue theorem, man, I thought we were going to get away from the residue theorem. I'm sorry, guys. I spoke too soon. We're very much still using the residue theorem. That's kind of the linchpin here, isn't it? K equals 1 to j, where j is the number of isolated singularities of f. Well, I guess it's not the number of isolated, it's what? It's the number of, I shouldn't say isolated singularities, I'd say it's the number, z sub j here, well, you guys tell me a second here, what's the, what should z sub k be here? So my note's got a z naught there. That's not right.
A 0 with f of z.
Right. So zk is either 0 or pole of f of z. Either one of those gives rise to a singularity of f prime over f, as that calculation over there shows you. And in fact, we calculated the residue because it simplified like it did. And so what this is 2 pi I sum over k equals 1 to j of, well, n sub k, right? So therefore, 1 over 2 pi I, the integral of f prime of z dz over f of z is equal to, you know, n1 plus n2 plus n sub, you know, however many there are, which of course is exactly what we mean by n sub 0 minus n sub infinity. Right, because we got a minus. We're using the convention that it's negative n sub j. N sub k is negative if it's a pole. It's positive if it's a 0 is our convention for this proof. So there you go. So that's all we got time for today. But next time we'll look at argument principle number 2, and we'll also try to understand this theorem a little bit more, because you can't understand it. If you go back to my original statement, I put down the differential of something. And this is related to a homework problem. Some of you did in the last homework. Some of you. And like this, that there exists, you know, this log. The differential of this thing is that thing. So when you integrate this, you're calculating the net change of this. And if we think about that some more, we can understand argument principle 1. But we'll start next class with that, chasing that. I do have the homework to hand back to you guys. So let me do that.